Okay, so last lecture we did was on concave mirrors, so now we're going to do convex mirrors. And convex mirrors look the same as concave mirrors, except the silvering, or the back, the silver that's painted on the back to make it reflective, is on this side. So this is now the back of the mirror, and this is the front of the mirror. And just to refresh, we're still going to do the two principal rays, which is the parallel to the central axis, or to the principal axis, and we will still do the focal ray, that is, touches object and focal point. So we're going to do the same two rays we did with the last one, but now because our mirror curves the other way, it's going to disperse the light. So the light coming in now is going to get bounced off and spread out, so that stuff on the top half is going to bounce off away to the top. Stuff on the bottom half is going to bounce off away on the bottom. If you can kind of think of it like this, here's a flat sheet. And if all the rays came in to a mirror that was flat, or a plane mirror, so they all came in parallel to each other, all the returning rays would go back out along that same path. But what we've done with a concave and a convex mirror is we have now curved the mirror. So all those rays that were parallel in concave, now they go in and bounce down, go in and bounce down, or go in and bounce up, go in and bounce up to some focal point. So my light rays, it's like I took that flat mirror and just curved it on its side. In a convex, that means it's going to spray the light out. So a concave collects the light to the focal point, where a convex mirror disperses or spreads out or dissipates the light over a larger area. So let's draw a couple of these. The math is going to be the same. Let's hit that idea too. You get a positive sign in the math if you are in front, if the location is in front of the mirror. And of course you get a negative sign in math if the location is behind the mirror. Okay, so here we go. Let's do our first convex mirror diagram. So let's do this. Let's make our curvature go this way. I'm going to move this line so it's a little bit more central. There we go. It's a little bit more central. So this is the front. Remember, this side is the front, and this side is the back. So we're going to put our object over here. And let's, just for math's sake, let's make this 15 centimeters. Now, where does our focal point go if we're on a convex mirror? Well, a concave mirror, remember I told you that the focal point is inside the curvature, so that's going to be true again for my convex lens. So my convex lens will have its focal point inside the curvature, which means your focal point is always going to have a negative sign. It's always going to have a negative sign because the focal point is actually behind the mirror, on the dark side or the back side of the mirror, where light doesn't go. And so for argument's sake, to make the math a little bit different here, let's make this 8 centimeters. So we got 15 centimeters. So DO, or SO, or P, whichever the book uses and whichever one you feel comfortable with, is going to be positive 15 centimeters. The object is in front of the mirror. But the focal point is going to be negative 8 centimeters because it is behind the mirror. And so we want to find where the image is, if it's bigger, smaller, is it real, virtual, and so forth. So the first ray we're going to do, just like we've done with the other ones, get this picture off of there now, so it doesn't get in our way, is we're going to have a ray that comes in, that comes in parallel to this principal axis. So it's going to come in parallel to our principal axis. And now what would normally happen is we would say the principal parallel to the principal axis goes out through the focal point. Well, you can see that the light has to bounce off the mirror, so it cannot go through the focal point. But because of the perception and the way that our eyes work, the reflected ray here is going to bounce off as if it went through the focal point. So we back trace through the focal point. Goes in, light does not go here. This is no light actually goes here, because that's behind the mirror. But our perception is that when the light bounces off, when we make our little normal ray, those two angles are the same, our perception is that the outgoing ray came from the focal point. That's what it appears to do to us. So that's our first ray. Now we've got to do our second ray. And so the second ray is a little bit trickier, because what we want with the second ray is we have to aim at the focal point. So I'm going to aim at the focal point here. Let's pick a color that's different than the ones we've got. I'm going to aim at the focal point. So let me get this. Focal point to mirror. I'm going to aim. Oops. That was too high. Let's see if I can get one of these. There we go. Here, coming in. Doop, 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 doop. Appears to. This is the focal ray, the one that quote unquote goes through the mirror. And so now the question is, where are those rays going to intersect? Well, here's the deal. That's the focal ray, but what happens when it hits the mirror? Let's refresh a couple of things. Just as with previously, hang on just a second, sorry, I reached principal ray. Just as with previously, I aim at the focal point. So I don't draw that ray on the back. What does that ray do? Aim at the focal point, comes out parallel. So the outgoing ray is going to come out, sorry, having a little bit of a computer funsies. It's going to hit the mirror right there, and it's going to come out parallel to the central axis. So this is the focal ray out. So our brain thinks it came from back here. Now notice, no light goes here. There is no light here. None. But our brain tells us there is light here. So where does our image occur? Well, you'll notice that these two won't intersect on this side. But where we perceive them to come from, they most certainly will intersect. So the tip of my arrow here is going to go right there. So there is going to be my image. So you'll notice they intersect where light doesn't actually go. But Ms. Wilson, if light doesn't go there, then how come we see it? Well, because in our brain, we did see the light that bounced off the mirror. We saw some light that bounced off the mirror. But our brain thinks that light all came from behind the mirror. We don't think of it as a reflection. Our brain doesn't process that. So what we do is we see it as if the image was coming from behind the mirror and the light's coming out through the mirror towards me. But what that does to our image, as you can see, it's going to make it a lot smaller. So our image distance is going to be a negative value. We don't know that yet, but it's going to be a negative value of some sort, and it's going to be negative because it is behind the mirror. So let's go ahead and classify these and do the math that goes with this problem. So it is a virtual image. It's a virtual image because there is actually no light source behind the mirror. So it's virtual. We can see from the picture that the orientation has the same orientation. Which we would call upright. It is smaller. And we can see that. The magnification. So that means magnification will be less than 1 when we do the math. And it is also closer to the mirror. Which means SI is less than SO. So closer to the mirror. Those are going to be the questions that they might ask you as a multiple choice. They might ask you to classify it, or they might ask it on a free response. They might say classify the image. So that would be how you classify the image. Now, how do we actually find out what that number is? Well, let's do the math. So here's our math. We're going to use the lens maker's equation or the mirror equation. It's the same equation, but the book calls it two different things, which kind of makes me chuckle. That's because it was found by two different people, but these things happen. So let's do this. So what is our focal? Well, it's -1/8. And that equals 1/15, 15 positive, and 1/SI. I don't know what the image distance is yet. That's what I'm trying to find. So, what am I going to do? Well, I'll take -1/8. I'll subtract the 1/15 to the other side. And because you don't really need to actually get common denominators here, we can go 1 divided by 8, and that's negative, minus, whoops, let me clear this, 1 divided by 8 minus 1 divided by 15. It gives me this decimal, negative point, whoops, sorry, I lost my decimal, 1916. The 6 is repeating, equals 1/SI. So, to solve this, what I'm going to do is I'm going to do the inverse of these two. So I'm going to go SI over 1 equals 1 over negative 0.1916, repeating. So I'm going to flip the fractions. That's exactly what you do when you cross multiply. So you can think of it either way. And when I do that on my calculator, I'll show you where that key is. On your calculator, this is your inverse key. So you'll notice that there's a 1/x here. On your calculators, it's usually an x to the -1 key. But if I invert this, it'll flip it and it'll tell me the answer. In this case, the distance is negative 5.2 centimeters. And as we expected, the number is negative because it is behind the mirror. It's closer to the mirror because our visual picture of that shows that. And so, negative 5.2 centimeters behind the mirror. If we wanted to know how much bigger or smaller, we would do this. Magnification is negative DI over positive DO. A lot of my students say magnification is dido or hi-ho, because you could do image height over object height. You could do it either way, but in this case, since we know this information, this is the way we're going to work the problem. So the magnification is negative 5.2, and my object distance was 15. So we're going to get about 1/3. Let's use that with our calculator. Yep. No. 5.2 divided by 15 is 0.346. So I'd go 0.35 no units on this, because magnification is just a multiplier. So what does this tell us? The magnification is positive 0.35. It's positive because the image is upright, and it's smaller because the image would be about 1/3 the size of the original object. So putting the object and image here makes the image be smaller. So you may ask, let's do another one. I'm good with that. Let's do another one. Let's do one where the object is inside the focal distance this time. Let's not do that. It's just for the sake of argument, I'm going to do it this way this time. I'm going to put my focal point here, which means this curvature needs to be quite a bit larger. And I'm going to put my object here. So let's put object distance 9 centimeters, focal point 18 centimeters. I'll put it halfway in. So how do we draw these? Okay, let's go back through. The first ray you draw is through the tip, parallel to the central axis. The incoming parallel ray will come out. Keep in mind, sorry, should not have done that. The focal point is behind the mirror, so it's going to be negative 18. This ray will hit the mirror and bounce off in such a way that appears to, there's our outgoing. Ooh, not straight. Sorry. Straight edges really are a necessary thing here. I'm getting it too steep. We're just going to have to estimate it, so y'all have to bear it with the fact that I don't have a straight edge. So this is our outgoing ray, but there is actually no light here. There's no light here. It just gives us the angle at which this ray gives us the angle at which this outgoing ray will match up. Like I'm just making it worse when I do this. Let's do this. I can use my line tool, and I can come back and do this. Here's outgoing. There we go. That's much better. I mean, I know it's still a little crooked on the back, but it's better than it was. Then our second ray is going to be the one that we aim at the focal point. So let's, because we can do this, we're going to aim at the focal point. So we're going to aim, let me get this. There's my ray. But remember that this ray does not go through the focal point. It simply hits the mirror and then it comes out. Should have been using this all along. It comes out. Oh my heavens. It comes out parallel. And that's the ray that we perceive coming back here. Get this lined up a little better. So now, where does our image occur? Our image occurs where this outgoing, once again, no light, but that's our outgoing ray. Here was our incoming, here's our outgoing. Out goes focal in, parallel out. This is parallel in, focal out. Where do these two cross? Well, these two cross so that the tip of my arrow now is here. Once again, it is behind the mirror. It's always, so convex is always going to be virtual because they're always going to intersect behind. It will always be a virtual image because the light doesn't actually go there. Now in this case, the magnification doesn't look like much magnification. Magnification might be 1. We'll figure it out. I'm just eyeballing it right now. It appears to be closer to the mirror, at least a little bit. And last but not least, it is upright. So let's check that with math. So 1 over F equals 1 over P plus 1 over Q. So it's 1 over negative 18 equals 1 over 9 plus 1 over Q. Now this is one where it's easy to get a common denominator, so I'm going to go ahead and do that. Negative 1/18. This is 2/18. This is 1 over Q. So that we get negative 3/18 equals 1 over Q. So negative 3Q equals 18. So Q equals negative 6 centimeters. So as we said, it is closer to the mirror than the original object was. If we want to do the magnification, be negative Q over P. So the magnification will be negative 6 centimeters over 9 centimeters. You'll notice these cancel out. And so we get 6 over 9, which is 0.67, is our magnification. So even though my image didn't quite do it, and it's because my rays are not all straight, it should be slightly smaller than the original, and it is slightly closer to the mirror than the original. Okay, I'm going to stop there for today, and hopefully you guys will come in during a Zoom on Monday nights or a Zoom during RTI on Mondays or Wednesdays, and we can answer your questions. Other than that, just email me and I'll let you know. Thanks. See you next time.